that is the bandwidth in your op-amp circuits. Now, I have already told you in the earlier classes what exactly we mean by bandwidth, but now how exactly you interpret the bandwidth, especially when you go with the compensation issues or whenever you go with the stability issues related to the operational amplifier, right? So, see, whenever I speak about the bandwidth, you know the lower cutoff frequency and upper cutoff frequency. Ideally, the bandwidth is infinite. When I take f here, okay, so when you take this as the gain, your bandwidth should be infinite. That means your lower cutoff frequency f1 should be at 0 hertz, that is DC. The upper cutoff frequency f2 should be infinite, right? That is the ideal case, but we never come across the ideal case. Now, the upper cutoff frequency is generally decided by the closed loop gain, that is your f2 is basically a function of closed loop gain. This is a very important point to be noted, and as long as the f1 is concerned, it can be 0 hertz, basically in the DC amplifiers or the directly coupled amplifiers. We have already seen what is the difference between the directly coupled and why do you require the different stages in between, right, for the purpose of the impedance matching and other things, right. So, directly coupled amplifiers are always subjected to, you know, the introduction of the noise or what you call it as the disturbances, right. That is the reason why we don't prefer the directly coupled amplifiers always, but if you have a directly coupled amplifier, you would have the lower cutoff frequency always at 0 hertz. But whenever I have the capacitor coupling, right. So, now when I say that my circuit or the operational amplifier circuit is likely to become unstable, the simplest solution is to connect the capacitor. We have already discussed about that in our previous discussion, right. So, when I connect the capacitor in my circuit, in what way it is going to affect the value of f1? This is a very important point to be noted. So, lower cutoff frequency or f1, okay, in some cases it is also called as fl, the lower cutoff frequency. It is given by 1 divided by 2 pi Ci into R in plus R naught. So, this is one important expression which you should always keep in mind. So, Fl is equals to 1 divided by 2 pi C into R. So, R is the thing but R in plus R naught, because everything will come into picture as long as the operation is concerned, right. So, now Ci is nothing but the coupling capacitor. So, where is the coupling? Between two stages. The coupling capacitor between two stages. R in, needless to mention that it is the input resistance of the next stage, and R naught is the output resistance of the previous stage, right. So, you have got the different stages wherein you have this coupling possible. So, the expression for the lower cutoff frequency from 0, it changes to 1 divided by 2 pi Fc into R in plus R naught. So, this is one important point to be noted, and the upper cutoff frequency, as I have already told you, it is limited by the gain or it is decided by the gain, and there we will define one more terminology which I think I have mentioned earlier, so it is called as gain bandwidth product. It is referred to as gain bandwidth product, which is also called as GBW. GBW, gain bandwidth product, and it is sometimes referred to as unity gain bandwidth. Please refer to these words carefully. Unity gain bandwidth, gain bandwidth product, or the unity gain bandwidth. What exactly is the gain bandwidth product? So, the very name itself suggests here, right? It is the product of, the gain and the frequency at which that particular gain occurs. Now, the question is here, now we have to again go back into our frequency response curve, something like this. Okay. Now, let us say that it is something like this, then it is something like this, then it is something like this. Okay. I have F here, then it is your ACL or AOL into beta, something like that, ACL. Okay. Now, if you draw this particular diagram, up to certain stage, up to certain frequency, your gain remains almost constant, and beyond that, right? So, you have the 20 dB per decade or 40 dB per decade decline in the gain, and this is very much possible, right? Now, let us say, let us take one example. Okay, now let me give you the example of our IC 741 only, which we generally come across. For IC 741, right? Now, when I that is the closed loop gain ACL, say it is equal to 10, the closed loop gain 10,000, right? So, this takes place, see, upper frequency of about 80 hertz. Okay, this is from the frequency response graph of your IC 741. A closed loop gain, it happens at a frequency of 80 hertz. Now, let us say that I have got 10,000, this value here, somewhere here. Okay, this is 10,000, and this has a frequency of 80 hertz. Okay. Then, if you proceed further, right? So, your ACL need to decrease here, as you can see from the diagram, and that is the common phenomena, right? As you go into the higher frequency ranges of the operation, the gain is going to decrease, right? So, now
has become say 1000, okay, at the of FH is equals to 800 hertz. Okay. Then ACL, the closed loop gain, has become 100 at a frequency of 8000 hertz. This has become 10. ACL has become 10, or let me I can write
followed by 5 zeros in all the cases. That is called as the gain bandwidth product. Right? And this gain with bandwidth product is also equal to unity gain frequency. This is called, it is also equal to unity gain frequency. The unity gain frequency in this particular case is 800 kilohertz, right? So this is one important point to be noted. Now, depending upon our requirement of the frequency compensation, if you know this gain bandwidth product or unity gain frequency or unity gain bandwidth from 0, it becomes the bandwidth only what we have taken, right? So that will give us an idea where exactly there is a line of the operational amplifier circuit going into the region of instability. So this is another important point to be noted, and we have one formula here to understand this particular formula. FH or ACL is equal to FU